Back to another Daishinfinity video. In this video, we're going to talk about the integral and the summation formula of the integral of 0 to 1 of the function x to the negative x dx. That is just equal to the infinite summation where n goes from 1 to infinity of the expression n to the negative n. Now those two expressions, if we would take it as a variable, they are exactly the same functions. So the function will be the same, but if we take the integral from 0 to 1, the area under the curve of x to the negative x is just equal to the infinite sum if you take the index n to be 1 and 2 and 3 and so on until infinity of n to the negative n. The value is going to be exactly the same, and I want to prove it to you with using different methods. So first of all, we can talk about the integral 0 to 1 of x to the negative x dx, and we can demonstrate it as an e function, and the e to the x, e to the ln of x, is just the same thing as x. Through this fact, we can also represent the x to be just this x to the negative x, so we just let the x to be the x to the negative x, so we will just have the integral from 0 to 1 of e to the ln of x to the negative x dx. And because we have another rule stating that logarithms with an exponent in an input is the same thing as the exponent times the logarithm of the input, and since we have an exponent on top, which is negative x, we can just represent it as an integral from 0 to 1 of e to the negative x times ln of x dx. Now we are stuck. Now we don't know how we can continue. But we thank Taylor for building us a infinite summation formula to demonstrate this e function in another way. The Taylor series expansion of e to the x is the same thing as the infinite sum where k goes from 0 to infinity of x to the k divided by k factorial. Or we can take n for the index. I don't really care about that. We will take n for the index soon. So if we would take the exponent to be this one, we'll just put all of the inputs inside. So we'll just have the integral from 0 to 1 of the infinite summation where n goes from 0 to infinity of minus x ln x to the kth power, to the nth power because I use the index to be n, dividing all by n factorial. Now since we have this one and I forgot to write the dx, we can factor out something outside. But before we do that, we want to do some small substitution. Now before we do some small substitution, we know the fact that the exponent rule a times b to the n is the same thing as a to the n times b to the n. So we can use this fact to distribute the exponent onto those two components. So we have the integral from 0 to 1 of the infinite summation n goes from 0 to infinity of negative ln x to the n times x to the n, dividing all by n factorial. The reason why I put the negative ln x together and not the negative x is because I'm going to do substitution in a short period of time. The substitution is going to be like this. We are going to let u equal to negative ln x. The reason I'm going to do this is it will allow me to use the e function again in the infinite summation. And since the infinite sum is conversion throughout the e function, every e function that has a negative exponent, it will go down rapidly. If you look at the graph e to the negative x, it will go down rapidly. So it will converge very nicely. And that's why we have a theorem called uniform convergence of the sum. And if that is happening, we can switch the integral sign with the summation. That's why I'm going to use the ln of x as the substitution, because we can do e to the both sides. Okay, so we will have e to the u equaling e to the negative ln x, which is just equal to e to the ln x to the negative 1. So we'll just cancel these two and we'll just get x to the negative 1. And now we can take both sides to the negative 1 power, so that we will get a plus 1 over here. And now we will get e to the negative u is equal to x to the 1, or x. Okay, so this is our representation for x, but we want to, and we have to, differentiate both sides. So we'll get du is equal to negative, will come in the front factor as a factor, and 1 over x dx. Now we're going to multiply both sides by negative 1 and x, so that we'll just leave us behind with the dx. So the dx is just equal to negative x du, where x was just equal to e to the negative u, so we'll just get negative e to the negative u du. So we can take a box and make a box behind it, and then just write the new type of thing we have. So we have something like this. We have the we have the integral from 0 to 1 of the infinite summation, where n goes from 0 to infinity, of the x to the n, negative ln x to the n, over n factorial dx. Now, we have substituted already, and before we substitute it, we have to take the boundaries of the integrals. So if x is going to 0, which is this bound here, then ln of 0 will go to negative infinity, but the negative infinity and the negative will become infinity, so u will become infinity, so u will approach infinity. This is the first condition. The second boundary, b, which is 1, is when x approaches 1. Negative ln 1 is just 0, so 0 is going to be u, so u will just approach 0. So we just go from infinity to 0. And since we have this uniform convergence theorem, I'm going to prove it in another video. We can flip the order of integration and summation signs, which will lead us into expressing an integral and summation formula like this. Summation from n goes from 0 to infinity of the integral from infinity to 0 of e to the negative u to the n times u to the n over n factorial times negative e to the negative u du. Now we know, we know from the fact that if you have something like b to a, where b is bigger than a, of f of x dx, it's just going to be the negative sign of the boundary a to b of f of x dx. Now you can put this negative sign on this side. It doesn't matter what you have in the textbook, but right now we just want to focus on this one. So we're just going to use one negative sign. And where can we find a negative sign? We can find a negative sign over here. So this will change the boundary 0 and infinity, which will lead us to this integral. So we will just have the infinite summation where n goes from 0 to infinity of the integral from 0 to infinity of e to the negative u to the n u to the n divided by n factorial times e to the negative u du. Now what we are going to do is we are going to take e to the negative u to the n, take the exponent rule. We know that a to the n to the m is the same thing as a to the n times m. So e to the negative u to the n is the same thing as e to the negative un, and e to the negative u times e to the negative un is the addition of those two. So we're just going to simplify the e functions. Now we're just going to do this by writing all of this and then taking e and then factorizing the negative u. So we will have n plus 1 u to the n over n factorial du. Now what we can do is we are talking about an integral, and the integral has n factorial as a number, as a constant, and the constant can be outside of the integral through the integral formula statement. So we can put the n factorial outside, but not outside of the summation, because the summation has the n inside as an index. So we just have to write down the summation n is equal to 0 to infinity 1 over n factorial times the integral from 0 to infinity of e to the negative u to the times n plus 1 times u to the n du. Now what we are going to do is we are going to see and observe this integral and see, okay, what can we find, what kind of patterns can we find. Now, especially this integral reminds you about the gamma function. The gamma function, any gamma function, gamma of x, states that the gamma of x is the same thing as the integral from 0 to infinity of e to the negative t times t to the x minus 1 dt. So we want to have u to the n minus 1 being equal to t, and n is n to be x minus 1 and u to be t. In order to do this, I'm just going to let u times n plus 1 equal to another variable. So I'm just going to pick another variable, which is going to be s. Just pick s as another variable. S is equal to u times n plus 1. So ds. And now be careful, u is the variable we are talking about. So n plus 1 is just a constant. So we just leave the constant and just write du over here. And so we know that du is equal to ds over n plus 1. And we also know that u is equal to s over n plus 1. Throughout these informations, we can just calculate the normal formulation, the summation from n going from 0 to infinity of the of 1 over n factorial, times the integral from 0 to infinity. Now we're going to talk about the e to the negative s times, now we are writing the u. U is equal to s divided by n plus 1. So s divided by n plus 1, and now all the thing to the n power. And now we're going to multiply by du, because now we have the du now. I'm sorry, du is gone now. We are using ds. So ds is equal to du times n plus 1. So du is equal to ds over n plus 1. So we're just going to write ds over n plus 1. Very complicated, but somehow interesting. So now we have a similar thing, like here we have another constant. We can put it outside of the integral by just saying that we have 1 over n plus 1 to the n, and another n plus 1, which is to the first power. So we would have 1 over n plus 1 to the 1 over n plus 1 to the n plus 1 power. And we'll take this one out of the integral. So we will have the summation n goes from 0 to infinity of 1 over n factorial times n plus 1 to the n plus 1 times the integral from 0 to infinity of e to the negative s times u, sorry, am I right? Times s to the n ds. Now this is almost similar as the gamma function. Let's recall the gamma function. The gamma function, gamma of, let's say, n, is equal to the integral from 0 to infinity of e to the negative s times s to the n minus 1. And now you do the ds. Now we have n. So we just plug in the n plus 1 here. we just plug in the n plus 1 here. So this will be n minus 1 plus 1, which will just equal to s to the n and e to the negative s. So this whole thing is just equal to the gamma of n plus 1. And we know through gamma functions that gamma of any number n is equal to the number n minus 1 to its factorial. So it means that gamma of n plus 1 is equal to gamma the n plus 1, and now we minus 1 that one to the factorial. So it will just be n factorial. So this is just n factorial. And since we have finished calculating all of the integral, we just have the summation where n goes from 0 to infinity of 1 over n factorial times n plus 1 to the n plus 1. And now over here on the numerator, we have times n factorial. So n factorials will cancel out without leaving any problems because n factorials never equal to 0. And now we will just have the infinite summation where n goes from 0 to infinity of 1 over n plus 1 to the n plus 1. Now to get the original form, we just have to put the index just by one number higher. So we just let n equal to 1. So we have to let those both numbers go down by one index. So we will just have the infinite summation where n goes from 1 to infinity of 1 over n plus 1 minus 1 is n, and n plus 1 minus 1 is also n, so we'll just have n to the n, which is just equal to the infinite summation of n to the 1, n is equal to 1 to infinity of n to the negative 1, sorry, n to the negative n. So this is just equal to the whole integral 0 to 1 x to the negative x dx. And now we have just proven that those two are equal. So I hope you understood and enjoyed this video. Please like and subscribe to my channel, and we'll see us in the next Daishinfinity video. See ya.